Today we are going to do section 4.5, the chain rule. Now to do the chain rule, well, first let's look at what it says. Okay, the chain rule, theorem 4.8, which says that if you have x equal to g of t, y equal to h of t are differentiable functions, and z equals to f of x of y is another differentiable function, and then if you plug x and y in terms of t into the z function, then you get a big pile of functions, right? And if that is the case, then the derivative of z equals to this equation, which is partial z partial x times dx by dt plus partial z partial y times dy by dt. So, and now all that sounds a bit confusing. So before we prove the theorem, I want to start with an a sample, okay, of what this thing looks like. So my sample is that, let me write down the sample. So here is a sample of what the theorem looked like. See, the sample talks about x is equal to gt. Okay, so I came up with I made up this example where I decided we'll let x equal to 2t. Okay, similarly, y, which is h of t, will be 3t squared. And where I chose t0 to be 1. Now, if t is at 0, then the value of x0, which is x at t0, would be 2 if you plug it in, right? And similarly, y0 would be 3. And then, so the next step we're going to do is figure out what dx by dt is. Well, that's a quick figure out, right? Dx by dt from here is 2. Dy by dt from here is 6t. And then we are evaluating stuff at t0 equal to 1. So at t equal to 1, dx by dt is still 2. Dy by dt is going to be 6. Okay, so far so good. And this is just our sample. Now next we'll figure out our function f. Okay, f, which is equal to z, right? And I made up this function. We'll call it x squared y and xy cubed. Why? I'm just coming up with a sample. Okay, so you get familiar with what we're going to be talking about in proving the theorem. So here's our z equals to f of x or y, etc. And then we'll do the partial f partial x. Now partial f partial x is a partial derivative with respect to x of the function f, okay, which is also called partial z partial x, okay, because z is f of y, which is also called fx of x and y. Now by now you're probably wondering, why are there so many names? And well, it happens all the time. It's no big deal. You know, like a guy who's called Jim Smith, he might be called Mr. Smith, right? Or he might be called Jim, or he might even be called Jimmy. Happens, okay? So we have three things describing one exact object. That means three names describing one object. Nothing wrong with that. Just remember that everything here means the same thing. The partial derivative of the function, this function right here, with respect to x. So I did the partial derivative and I calculated this. With x, that will be 2xy, right? And then this will just have y left. Okay, so that's the partial fx of xy. Now next, fy of partial y, same thing. Partial f partial y is the same as partial z partial y, which is the same as fy xy. Okay, and then we do the derivative, and at this time with respect to y, so then you get x squared left, and then you get 3y squared times x, which is right here. Okay, so far so good. And finally, we're going to plug z is equal to fxy, whereas x is equal to 2t, right? And y equal to 3t squared. So what is z of t? So z of t is we're going to plug this stuff right in the f. Okay, if you plug it in, then we get this pile of stuff out. Okay, this is xy in squared, etc. And then if you add it all up, and if it's not wrong, then I hope that I didn't get it wrong, but it doesn't matter. Okay, the point is it's something to do with t, right? So then you get the answer is some function of t, And then the derivative, then you take the derivative of this thing, then you get something else of t, okay? And oh, I forgot to mention over here. Now, the partial derivatives, we will need to evaluate it at our specific point where t equal to 1, in which case x is 2 and y is 3. Okay, x0. So we need to evaluate what is fx of x 2 and 3. So we plug 2 and 3 in fx partial x here, and then I came up with 39 if you plug 2 and 3 for x and y in this equation. I hope I got it right. I don't know, it doesn't matter. It equals to a number is the point. Similarly, fy, and when I plugged it in, equal to this thing. Okay, and yeah. Anyway, so that's what I got, and that is a sample of a function that we will be talking about when we prove the theorem in general. I want you to look at all this because that way you get your brain to wrap around what any of this stuff means and not get lost by the terminology and the symbols and all three things mean the same thing, that sort of thing. So now that we have gone through all this, we are ready to prove the theorem. So in theorem 4.8, we're given that if you have a function x like that and a function y, right, like in terms of t, and then the function z, okay, all of which are differentiable everywhere, then the combined function, this one right here, will be differentiable, okay, and then the derivative will be the dc by dt is going to be given by a nice symmetrical formula. That's nevertheless quite a bit of work to do, but at least it looks nice. So the first thing we are going to prove is that such a function given, okay, something like that, will be differentiable. Now to prove something is differentiable, here's the condition. We have to write this function out, okay, in terms of some kind of a e, and with all these numbers, and where e, we have to demonstrate that e divided by this square root thing is going to go to 0. In the limit. If that is the case, then this function will be differentiable. So that'll be our first job. Now, before we go forward, remember that fx0, y0, which I forgot to mention, okay, fx0, y0 is just this function with x and y being evaluated at these values, okay? So it will also be called z0 and also be called a z of t of 0 because it happened when t is 0 and which made x and y a certain value. And if you plug it in here, here's the function, you will get some kind of a number for it, in my case 66. So so that's that. So that's what we're trying to do here. This is a number, okay, which is over there somewhere, right here, okay? Here's a number. So we have a number times x minus x0, which is 2 in our example. And then this is another similar number, fy, okay, that you can calculate. And then multiply by y minus y0. And eventually, we end up with something called e. And we have to prove that this limit approaches 0. Now the next step, we are going to plug the t stuff in there. That is z of t, okay, which means c used to be f and x and y, right? We'll plug it into t, which is this thing right here. And now in a sample, it's 90t squared. Okay, so we have c of t minus c of t0, which is c of t0 is this stuff, which is 66 in our example. And so we'll subtract that, which will equal to, we're doing this thing here, but we'll plug x and y into the function, the t function. Okay, so we'll plug all the t's in here. So this thing is still a number, right? This is the partial derivative at x0, y0, which is that number right there. But the x of t, we'll plug the function in here. And then x of t0, that is just a number, which is in our case just a 2. And then the same thing with y. Okay, this is just a number, which is over there, 58. But this is y of t, which in our case is 3t squared. We'll plug it right in here, following this formula. See, y minus y0. So now we'll have y of t minus y of t of 0. That is, that is still 3. And then plus e, where E used to be in front in terms of x and y, and now E will be in terms of x of t and y of t. So with that, we have shoved everything instead of x and y, now we shoved the t's in there, okay? So now is everything is in terms of t now. The next step, we're gonna divide by t minus t0 across the board. So we have t minus t0 here, and here, and here, and here. Okay, so everything got divided by t minus t0. Why? Now, if you look at this thing, what does this thing remind you of? This is this is the derivative of z with respect to t evaluated at t equal to 0, the same as here, right? This is the derivative at t0, not t equal to 0, at t0. And same thing here, this is y prime at t0. And this is, well, that's whatever that is. So let's look at the next page. As you can see, we are going to take the limit, okay? And when you take the limit of all this stuff, then then everything magically turned into this. Let me write it down. So I have it written out right here. So dc by dt, which as you remember, in our case is this number right here, 360 t squared, done by that, right? So dc by dt end up being the partial of x at x equal to 0. Here's our sample, right? And then times dx by dt, which is this thing. This thing, and this is the definition of dx by dt, which exists and is continuous because we already agreed that x and y, x of t and y of t and f of x, y, they're all differentiable and everything, okay? Everything is super nice. So this derivative, this is the derivative, which is called dx by dt, right here. And similarly, for the y, same situation. We have f of y, okay? And that's just a number, fy, x0, y0. And then multiply by dy by dt. That's this thing, all right? And then plus the limit of the error. Now, the error, of course, we don't know where that's going yet, so we'll copy it down here. But it's also divided by t minus t0. Now, what is this thing right here? This is exactly partial f. This is partial f, partial x, right? And then times dx by dt. And then this is, of course, partial y, partial f, partial y, okay? And times dy by dt. So you notice, what is that? That is exactly what we're trying to prove, okay? This thing right here. See, dz by in the theorem, dc by t equals to partial z. And remember, partial f, I should write it differently. Partial f, where's my partial f? Partial f, partial x is the same as partial z, partial x. Okay, so let's write it exactly like the book has it. So this is partial z, partial x. And similar, this one is partial z, partial y, because partial z is the same as partial f, as we have established earlier. See, partial f, partial y is the same as partial z, partial y. So we'll write it like that. And then, as you can see, so it's partial z, partial x, dx by dt, partial z, partial y, dy by dt, and that's our formula that we are trying to prove. Except this, right? We still got this. We got to prove this thing goes to 0. Otherwise, this is not gonna mean anything. So how do we prove that thing goes to 0? Then we move on and keep going. So now we are stuck with doing this. Like, how do we prove this thing go to 0? We don't know anything about it. Actually, we know a little bit, okay? We have this. This is given to us because the f of xy is differentiable, so we got this. This limit go to 0. Now, how are we going to get that into this, right? And here's this is where your book comes up with a very neat trick, okay? Now, what we're going to do is pull this neat trick. Here's the limit, okay? And what we're going to do is divide and multiply it by the square root of x minus x0 over here, on this side over here, and y minus y0. And you divide it and then you multiply it, so then you haven't changed anything, okay? And now you see where this is going. The next step, we're gonna split that product, the multiplication result, into two limits. There's a rule that says you can totally do that, okay? In 2D limits, it's just like 1D. You can just pull, if you have a limit of product, you can just stick a limit on each product. So now you're seeing where this is going, where t is the limit that t is still going to 0, but the first limit has only x and y in it. So when t approaches t0, not 0. When t approaches t0, that just means x and y approaches x0. See, as t goes to t0, x goes to x0, and y goes to y0. So you can rewrite that limit as x and y goes to x0, y0. Like, let's see, which side is it on? Oh yeah, over here, see? And that, what is that? That's exactly the limit that we are required to think about. And then the other side has the square root, okay, over t minus t0. And we'll think about that for a second. But look at this. This is exactly what we're given. This thing equals 0. So we're having a product that's multiplied by the limit of something else, and it's already 0. So we are almost home. Now, what about the other thing? Do we have to prove that's equal to 0 too? No, we don't. Why? Because we're talking about multiplying here, okay? All we have to prove is the other limit is finite. It doesn't go to infinity, because then we're stuck with a 0 times infinity situation, and then we're stuck. So we just have to prove that the other thing is a set number. It doesn't matter if it's a billion. As long as it's a set number, we are home free. So how do we prove that thing is a set number? Then we're going to pull another trick, okay? So the other part, then, the next step is that we are going to do some algebra now. Some algebra tricks. We're going to pull the square root sign all the way down so it covers the denominator too. So then the t minus t0 becomes squared. The next step, we're going to break it up into two fractions. Okay, so you have two things there. And what does that look like to you? That is the derivative of x with respect to t, right? Because x is a function of t, as we were given before. So the derivative will look exactly like that. So the final step is what we're doing here. See, it becomes the limit of, you notice the limit got inside the square root sign, and it even got inside the squared sign. Okay, so the limit is completely inside now. And you see where that limit is going? That limit is the derivative of x with respect to t, and the other one being the same thing, dy by dt. Okay, and as we have shown in our sample, dx by dt at t equal to t0 is a fixed number, and so is dy by dt, because those are all differentiable functions. So everything works out nicely. Nothing's going to infinity or breaking or anything like that. So therefore, this particular limit is a finite number. And being that it is being multiplied by 0, remember that's what we were doing a little earlier. Where'd it go? Which one is multiplying? Right here on the top row. See, those two are being multiplied, and the first thing on this row is 0. Therefore, this thing goes to 0. Okay, and we have finished our proof. Now, the last thing we should mention that we only proved it on a random point called t0, but we didn't say where t0 is. And being that x and y and f of xy are all differentiable everywhere, then it follows that this theorem works for everywhere. Okay, that anything is properly defined and stuff. And that marks the end of this proof. As you can see, this proof has a lot of symbols, and at first sight, you might feel like, ugh, why there's so many symbols? But if you, whenever you have things that have way too many symbols, it's a good idea to design a sample for yourself, like this one. I just made it up, right? And then write out every single thing so that you have a concrete idea of what are we talking about here, okay? So despite the fact that there are a million symbols, most of it is, there's not much to it, like this thing, okay? Fx, x0, y0, how many symbols are there? All it is just a number. There is in other words, let's not think of it as more harder than it really is. This proof is, as you can see in the end, a very simple proof, but it does have a zillion symbols, and which is why I'm not writing it all out, because that's going to wear out my hand. And so that's that. Now that we know this, okay, we know that this nice fancy formula, dz by dt equals a partial z partial x times dx by dt plus partial z partial y times dy by dt. Now that we know that, we need to do it. And doing it is going to be somewhat tedious. Okay, so please use the chain rule. It's tedious, but you follow the same laws. as you have always done. Okay, so please do, what is that? Example 4.26 as part of your homework. It goes pages. Okay, and then next is what? Okay, so that's that. We'll finish this section in the next video.